Biostat 6611, skills for the rest of your life, bootstraps and probability, it's the bread and butter, baby, what's your jam?
Welcome to another lecture of Biostat 6611. Today we're going to be talking about the Neyman-Pearson approach to data analysis, or what we will see as Neyman-Pearson trade-offs. We're first going to just briefly touch again on hypothesis testing and review Fisher's approach to data analysis, and then introduce and discuss the Neyman-Pearson approach to data testing. So, hypothesis tests. Hypothesis testing is the framework we use, or the method we use, to make inferences about a population quantity based on a sample of data. We'll see that we begin with a statement, or what we will call a hypothesis, about the population, and then use that data from a sample to determine if our hypothesis is supportable or not. In other words, a hypothesis is a claim or statement about a population parameter, or potentially multiple parameters at the same time. The way we formally test this then is through a hypothesis test, a statistical method we'll use of various types, and especially exploring in the next few weeks. For example, we may have a situation where the recommended daily allowance for zinc for males over 50 is 15 milligrams per day. Perhaps a study was done that found a sample of 115 men between 65 to 74 years of age had an average intake of 11.3 milligrams per day with a standard deviation of 6.4. We might ask the question, does the study indicate that there's too little zinc in the diet for these men, and perhaps more broadly for the population of 65 to 74-year-old men? Now, we had a lecture before this looking at Fisher's approach to analyzing data. Just briefly to summarize there, the approach proposed by Fisher really focused on this idea of what we can think of as a permutation test, which is also something we'll explore in a few weeks. Fisher had this idea of calculating what we would think of as a p-value. In his case, he only really defined what we would think of as the null hypothesis, because when he's shuffling around all the data and doing his little permutation thing, really he's trying to break any relationship that may exist in the data by randomly shuffling it. Therefore, his comparisons, though, are only done a posteriori, or after you do a study and collect some data, you shuffle everything up and compare it to the sample you actually observed to see how extreme it may or may not be. As we'll see, there's a lot of similarities and some strong differences with Neyman and Pearson. So, Jerzy Neyman and Egon Pearson. Neyman was a Polish statistician who eventually taught at UC Berkeley in California, whereas Pearson was a British statistician who taught at the University College London. They were great collaborators, and they together felt that Fisher's approach was lacking in some key ways. It turns out Fisher and Neyman-Pearson were somewhat low-key rivals as well, or maybe not so low-key depending on the resources you find out there about the development of these approaches. What they sought out to do, though, was to develop an approach that was more mathematical and focused on some a priori considerations. So rather than Fisher's a posteriori approach, trying to take into account things that we can look at or assume or build into a model before we even do the study. And so this leads us again to this idea of a null hypothesis, and that's really the first step we have when we're going to, let's say, do a study, at least the way Neyman and Pearson are framing it. The null hypothesis is a claim that is initially assumed to be true and will have some form that's similar to something like there is no change between, let's say, x and y, or maybe there's no difference or no effect of or no association with. So we have most of the time this hypothesis stated in a null way where there's no difference. H naught then is where we place the burden of proof for our data. It's what we would actually like to disprove in practice based on the data we collect. Now this is where we start to differ from Fisher's approach in a very marked way. In the Neyman-Pearson approach, we not only have this idea of a null or permutation distribution, but we also will state an opposing or alternative hypothesis to the null. And you'll often see this indicated as H sub 1 or H sub A. So H1 contradicts H0, so that both cannot be true at the same exact time. And this is really the statement we would hope to prove as the truth. The form of H1 is similar to H0, but generally we would indicate it maybe with a less than or greater than or not equal to in place of an equal to sign. For example, let's assume that we take the heights of everyone in class. And so maybe we have a null hypothesis H0 that the mean height is going to be 5.5 feet. Now we might then say we actually want to prove otherwise, that we're actually a class of really tall people. And so maybe our alternative hypothesis is that mu is actually greater than 5.5 feet. Or perhaps we don't want to make a decision about the direction of it, and we might say something instead like mu is not equal to 5.5 feet. Here we can see, though, that either way we define that alternative hypothesis, it cannot both be true that mu is 5.5 feet and is either not equal to or greater than 5.5 feet. This then leads us to something you may have heard about referred to as type 1 and type 2 errors. And so these directly come from the way Neyman and Pearson framed this problem of having a null and an alternative hypothesis. So we collect that data assuming that null hypothesis is true. We then are going to test that assumption of truth and make a decision about the ultimate veracity of that claim. So really, based on our data, we have 4 possible outcomes we could make. In the first case, H0 is actually true, and we fail to reject H0. In the second case, we have an incorrect decision. H0 is true, but we reject H0. We'd say there is some difference when there's really none there. Number 3 would be the case where H0 is in fact false, and we failed to reject H0. So again, another incorrect error. There was something to detect there, a difference was present, but we missed it. And in case 4, we have another correct decision where H0 is false, and we correctly rejected that null hypothesis. The 2 scenarios that are incorrect conclusions represent then the idea of type 1 and type 2 error. Type 1 error is the probability of rejecting H0 when it is in fact true, or outcome number 2, and this is usually considered the more serious error we could make. Let's imagine for a second that we're investigating a pharmaceutical agent in a clinical trial. If we were to incorrectly determine that there was a benefit to the drug when none existed, we can think about the ethical implications for that. The people will now be given a treatment that does not work, and it may therefore prevent other actually effective treatments from moving forward, or could expose people to negative side effects that, if we assumed it were working, may be acceptable, but with no benefit would be unacceptable. This then is in contrast to a type 2 error, where it's the probability of failing to reject H0 when it's false, or outcome number 3. Obviously, this is a choice we also don't want to make, but people generally are less worried about this one because if we miss an effective drug, let's say, that is a bummer and it's very sad, but at least we're not exposing people to the ineffective treatment. And later on, when we talk about power and these other concepts and how to derive them in the properties of future studies, we'll see that there's a give and take in this balance of type 1 and 2 errors. So a couple ways we can remember type 1 and 2 errors in a little more comical fashion. We have this graphical example of a doctor meeting with a patient. On the left-hand side, we see a doctor committing a type 1 error, or a false positive, telling the patient, who appears to be a man, you're pregnant. Clearly, that should be a false positive. Versus on the right, we have a picture where a woman looks visibly pregnant, and we're committing a type 2 error. The doctor says, you're not pregnant. It's just a basketball. In that case, it's a false negative error. We've missed that difference or that effect that's taking place. Another way that we might be able to think about this is the story of the boy who cried wolf. So remember, in that story, we actually have a type 1 and a type 2 error committed in that order. First, when the boy cried wolf, everyone believed him, but there actually wasn't a wolf present. Next, when the boy cried wolf and there was one, they didn't believe there was one there. So if we substitute effect for wolf, we've now replaced it where first people believe there's an effect there when there wasn't, a type 1 error, and then they didn't believe there was an effect there when there was, a type 2 error. And this brings us to one of the most fundamental concepts we have in modern statistics, and we'll see how this plays into our modern paradigm in the next lecture. But we're going to introduce these concepts because they're what Neyman and Pearson came up with. So again, based on the data we're collecting to address if the null hypothesis is true or not, we're going to make one of those 4 decisions. Now it is important to note first off that there is a slight difference between reality and what we decide. Reality would be the case where we collect all possible data that exists in the universe and without a doubt can decide if the null hypothesis is true or false. In actuality, in practice, we can't make claims like we accept H0 or H0 is true because we're basing this off a single sample. So instead, we will say things like we reject or fail to reject H0 based on the data we've observed. So let's take a second to break down some of the new terms that we'll see throughout the rest of the semester and also in these upcoming slides about how we do testing and calculate power and things like that. First off, we can note we do have our 2 cells here looking at the bottom right and the top left of our 2 by 2 table where we make the correct decision. We either find H0 is true and we fail to reject H0, or in the bottom right we reject H0 when H0 is actually false. There's an effect to detect. Now here we can see we have then on the off diagonal the cases where we've made a mistake or done that type 1 or committed a type 2 error. And here we see we actually have a special way we define these with the terms alpha and beta. So we'll see that alpha is going to be defined as the probability we make a type 1 error rate. Again, because people are more concerned generally with a false positive when there's actually no effect there, we want to set alpha to be low. And traditionally, you may have seen the value less than 0.05. This can also be thought of as the level of significance we're attempting to achieve in the case of the Neyman-Pearson framework. In the top right, we then see the probability of committing a type 2 error is defined by what we'll say beta. We can see then that alpha and beta have these connections with the correct choices we might actually make, where 1 minus alpha is the level of confidence we have in our conclusion, and 1 minus beta is going to represent our power, or the probability we make a correct decision that an effect is truly there when it's present. Now this brings us to an extremely important assumption. Neyman and Pearson assumed that alpha and beta, these probabilities of committing a type 1 or type 2 error, were in terms of what we'll call long runs. In other words, over infinite repeated samples, we would expect to see alpha or a type 1 error occur alpha % of the time, and we would expect the probability of a type 2 error to occur beta % of the time. So if alpha is 0.05, 5% of the time. Unfortunately, this is an unrealistic assumption. First, we actually can't do infinite samples because we just have a finite amount of time and hours in the day. And unfortunately, on top of that, in practice, we often don't even try to replicate studies even more than once. This can be thought of as the fact that people will do a study, they'll get a result and publish it, and then we may not even try to reproduce the finding. Fortunately, we actually can leverage these properties in our simulation studies because we can do a made-up scenario where we quote-unquote know the truth because we said it and simulate as many samples as we desire. And if we were to enter a world of research where we actually did reproduce studies, we can imagine again that the probability of a type 1 or 2 error would be that approximate % of the time we make the incorrect conclusion over multiple repeated experiments. So let's briefly revisit our 4 possible outcomes in the Neyman-Pearson framework and map those back to alpha and beta, power, and levels of confidence. Here we see that when we make the correct choice, H0 is true, and we fail to reject H0 in our sample, we have 1 minus alpha, or the level of confidence. In case 2, we make that wrong choice where H naught is true, but we incorrectly reject the null hypothesis and believe there's an effect. And so that's alpha, our probability of that type 1 error. In case 3, we have again the incorrect choice where H naught is false and we fail to detect that difference in an effect. So that's beta, our probability of that type 2 error. And then we have, for our fourth scenario, H naught's false and we correctly identified there's a difference, or the power 1 minus beta of a study. It is useful to note that 1 and 4 are both correct decisions, but they represent, again, different probabilities of making a correct decision with respect to power to detect a difference and the level of confidence that no difference exists. So how do we actually make our decision with Neyman-Pearson? Fisher had his p-value idea that he used. Neyman-Pearson didn't necessarily agree with that, and instead they came up with this idea of a rejection region, or what they may call in some places or textbooks a critical region of a test. It represents the range of potentially observable values for which we would reject H naught in a given study. This region is defined based on that desired alpha level we want to control, the probability of a type 1 error. So for the mean, it would be defined as something very generically as the probability that the mean is between critical value 1 and up to critical value 2, assuming H naught is true, and that will be equal to 1 minus alpha, or again, if we're assuming the null is true, that level of confidence. We can derive this for different tests and properties, and so one nice one we can just see briefly is deriving the rejection region for the mean, because we can assume that x is normally distributed, and so by the central limit theorem we know that the sample mean will also be normally distributed, where instead of this variance sigma squared, we'll have sigma squared over n. So let's assume that the null hypothesis is that H naught is equal to mu naught. So some value, the truth is mu naught. We can solve for the rejection region here by leveraging the standard normal distribution, or in other words, remember from the normal distribution lectures, Z can be thought of as our statistic that is a normal distribution with mean 0 and a variance equal to 1. Well, here what we see set up is that we have our alpha term, that desired type 1 error rate, or our level of confidence in the way we're framing it here is 1 minus alpha equals a Z statistic on either side that will be symmetric because we are dealing again with the sample mean, which is the middle of our normal distribution. And then we're going to take our middle term here and just write it in terms of how we can transform any given sample onto the standard normal space where that mean is 0 and the variance is 1. Again, though, this is all under the assumption that we see here given that H naught is true. So that vertical line there is saying given whatever to the right is occurring. The next two lines here are just rearranging the terms, doing a little algebra. And so we see in this second line here where I just drew an arrow, we multiply across the problem by sigma over square root of n, so that we now just have x bar minus mu naught in the middle there, and then we add mu naught to both sides of our inequalities, and we end up with a term here which is the true value under the null distribution that we're assuming, minus a value from the standard normal distribution at 1 minus alpha over 2, which we'll note on the next slide, multiplied by that standard deviation over square root of n, and it's symmetric on either side. So really we can think of it then as C1 and C2 given H naught is true. What we've essentially calculated then is a confidence interval around the null hypothesis value of mu naught. Let's just briefly introduce an example of what this might look like in the Neyman-Pearson framework, because remember, again, we don't have a p-value that we might use to actually determine the significance of our test. So let's assume we conduct a small study measuring cholesterol that involves 12 individuals. We take a sample mean of the cholesterol and we see it's 217 milligrams per deciliter. The variance is 46 squared, And the assumed null value for a population, let's say, mu naught, is going to be equal to 211 milligrams per deciliter. And for the sake of this example, we'll assume alpha equals 0.05. One thing we can note when we're going to plug these values into the equation from the previous slide is that that z statistic that we're working with, 1 minus alpha over 2, right here, if we plug that in here, we get z at 0.975, which is equal to a value of 1.96. Briefly just sort of sketching out the standard normal, we have 0, 1.96, and what we're saying is that 97.5% of the normal distribution is to the left of that point. We can also check this in R by using the qnorm function, putting in 0.975, and we'll get approximately 1.96. Now, actually looking here below at our values, we'll just plug in everything from our example, do the math, and we'll wind up here with a 95% level of confidence that the mean will fall between 185 and 237 milligrams per deciliter. In other words, we would fail to reject the null hypothesis in the Neyman-Pearson framework if our sample's mean is between 185 and 237. Therefore, in our sample, since we observed a mean of 217, we failed to reject the null hypothesis that the sample came from a population with the mean cholesterol level of 211 milligrams per deciliter. So with this example, we get a brief introduction to how Neyman and Pearson would actually apply their framework, and we see the differences here from the Fisher framework, where he would permute values and try to look at it in a different way. So let's briefly summarize their approach before we move on to the next lecture, where we introduce how we actually do statistics more often than not in the modern day and age. We did hopefully note some similarities to Fisher's approach, but there are many differences. First, we explicitly define an alternative hypothesis. There are also no actual p-values included in the way Neyman and Pearson proposed their framework. They also assume repeated long-run sampling for properties like type 1 and type 2 errors. And also one thing that they were huge proponents of that we didn't talk about really that much is that alpha and beta should be defined a priori, or before you even do and design a study. And then you design the study on those features and calculate how many participants you might need to actually observe and detect a difference. With this information, we'll see that in today's way we practice a lot of statistics, there'll be a lot of crossover and an amalgamation of the Fisher, Neyman, and Pearson approaches, which we'll see in our next lecture.